Thank you for the intro. Today I wanted to talk about prompt optimization that I have been doing in my recent years, which is quite important for many academic and industrial applications. This is about automated prompt optimization. We hear a lot of things nowadays, like about prompt engineering. Everybody comes up with a better prompt. Like if you use this, this is kind of the silver, the ultimate prompt that you can use for this task and so on. Uh, However, there's a ton of these kind of prompts in general. So there is a better and systematic way of doing this. The idea is pretty simple, actually. Like overall, if you can measure it, you can optimize it. So this is the overall idea behind this prompt optimization. Um, I'm gonna do it. I'm gonna talk a few more sentences on this because I think I need to provide the like intro, the motivation. Um, when it comes to different like LLMs are part of like many programs nowadays. Like LLMs are not individual isolated services that you just use for chats. They are going into every kind of different programs, which makes the impact of this prompting even more important because if you use LLMs in different programs and applications, it doesn't change its behave, its like nature. They are still based on prompts. So the first important thing these are important is agentic AI systems. These agentic AIs again getting like they are going everywhere, like coding, especially like the most importantly, also like using as becoming your personal assistant or whatsoever. However, there are so many things that can that you need to optimize. For example, in agentic AI, one key part is you need to just call your correct tools. And how do you do that is really a difficult problem. Because when you ask your AI to just to do some task for you, it needs to find the correct tools. Finding the correct tools is not easy because you have a lot of tools and you need to find you need to use the correct tools if among those so many options. And these are all based on textual descriptions, like what the prompt does, what are the arguments to it, and so on. Another thing is these agentic AI systems, they have different components. They are which are connected to each other, and they all need to understand each of they need to each component needs to understand the output or like the requirements of the next step. So there is a like this is a long chain in general. Uh, there is another component which is a bit of a still growing field, in my opinion, which is the multimodal aspect of these agentic AI systems. Um, what is important for these parts is you need to understand what it is talking about. It's not for many application, it's not enough for an agentic AI to tell you there is something in this image, like like it is not enough to describe an image. You also need to understand what it is talking about. Otherwise, it is so easy for the model to hallucinate or like you're not going to have any control over the flow. So there is this kind of like places where the prompts are they matter a lot. Then so I hope this just gives a bit of a like the motivation why that is important, especially with this agentic AI setting. Um, there are a couple of papers that I have curated the rest of the talk from. However, so the one that is mentioned in the slide is the one that quite summarizes the idea pretty well. So you can have a look at it afterwards if you are like if you are interested in more details. So I'm gonna go into more details of how this prompt optimization works, like what are the like and what is the what is the overall structure and so on. So the overall framework is called the DSPy framework. So this the idea here is basically we separate the concerns. The separation is between the logic and the implementation. So the logic is the program itself, right? Like you write a program, basically, for example, for an agent, for a coding agent, it just uses your Git commands or like use your file system and so on. That's the logic. And the implementation is with the LLM calls. So basically the framework separates between those two. That's how it starts. The goal is uh, the goal is we want to update these prompts to maximize some downstream metric, and we don't have any access to these module level labels or gradients. All we have, so the assumption in the framework is you don't have any access to any internals of the program. All you have access to is basically the prompts or the LLM inference part. So which makes it pretty much applicable modular to any kind of LLM application that you can come up with. So this is how it looks like. In a nutshell, I'm gonna talk a bit more on how like what it does. But the summary is we are we need a we need some question answer pairs and a metric. So basically, some your question set, your question and answer set, and you also have a metric to measure how well it performs. Once you have such a data set, then you can continue. So the first step in this optimization is you need to first evaluate your candidate query. So the candidate here refers to a candidate prompt. As first you evaluate how well it performs using your metrics, and then you make a critic on top of this query, on top of this result. Again, this is like with LLM, and it just tells you basically what went well and what didn't went well, and the whole thing is happening in a loop, and which is the optimization loop. Um, of course, maybe I made it a bit sound easy. However, there is like some quite difficult, like some big problems here that we need to understand. First thing is about the proposals. Um, in the very first slide, I talked about everybody comes up with a different prompt, with different idea and so on. This is because LLMs are highly sensitive to the prompts or the noise in the prompts, or how you structure it and so on. What this means in practice is even if you have a, let's say, 1% change in a submodule prompt in an agentic system, it can it can cause a catastrophic failure in the later stages. And this happens a lot, by the way. Like if you just try to do any kind of agentic optimization with the agentic systems, this is kind of the first thing that is going to be super annoying to you. Um, so this brings us to a combinatorial problem because you can't enumerate all your proposals. So you need to be a bit smart here. You can't come up basically you can't enumerate all possible prompts so that you can optimize for it. And another big challenge is you need to like this is the credit assignment problem, which means that you need to understand what prompt contributed to the performance the most. If you don't understand that, then there is no way of telling what is going well because you need a signal, and the ultimate prompt is not going to be the best performing one, but rather a combination of the previous history. So we need a good way of that credit assignment system. There is one method which is called MIPRO. So MIPRO, there is gonna be so there are a couple of steps here that I'm gonna share and connect you to the overview that I shared previously. So the key part in the first step is the rationale versus raw data. Uh, Here the rationale is an intermediate latent step. So it's not an output that you're gonna use eventually, but it's like some intermediate step that's gonna lead us to the optimization. Um, so the rationale is basically forces the model to attend to the logic of the task even before it commits itself to an answer. What happens is it just simplifies the optimization pipeline for the LLM. And it starts with bootstrapping a few examples. Bootstrapping is a really nice method that helps a lot. Um, so basically, just use the rational among different demonstrations. Why this is okay is because inference with LLM is usually cheap. That's what motivates this like a bootstrapping approach. The second part is it's about this contextual proposal. The optimizer doesn't just guess the instructions. It uses an instructor LLM, and this LLM reads the data set and it identifies the common failure modes to suggest fixes. So what happens is this provides the proposal language model with relevant context, such as like what is inside the data. I'm gonna give you more examples once I just talk about the architecture. I hope it's gonna give you a better sense of what this means in practice actually. And also it gives an idea to the language model as a some idea about the program itself, and also like about some successful cases so that it can understand what's going well. The key idea here is, I think, the grounding. It basically understands the task uh, to set the context for the optimization. Basically, it's like a history, kind of a trajectory that keeps a track of what worked well and what didn't work well. It also adds some prompting tips. So these are some manual tips, basically, still they are there, but it's not much. They are super simple prompting tips, some sort of templates. Uh, and then eventually we get different instructions after this step. Uh, the uh, the idea with the proposals is to use a Bayesian surrogate function here, Bayesian surrogate model. Instead of like, for example, the alternatives is um, you could use some maybe random search, for example. That would be the naive approach to use here. However, it's gonna be like really, really difficult to search that space. Basically, this is a Bayesian tree search. Uh, the impractic like the difficulty in traceable search, it just comes from the fact that we can't afford to run the full benchmark for every candidate prompt. That's the limitation. In this specific approach, MIPRO uses these like cheap model because it's like super easy to run. It's not a deep model like a Gaussian process to predict how a product might perform. Then only runs the most promising ones on the real LLM. Um, Basically, so like on the underlying implementation is basically a tree structured optimizer for this Bayesian model. How it goes is you first basically sample your data and instruction pairs, and then you evaluate your pair. Uh, then you update your belief. Either you can lower your belief or increase your belief. Then rinse and repeat as a typical Bayesian process. Um, what could be simpler alternative to this? Just to highlight the idea, like you could be going greedy. Basically, you just use the highest score. This doesn't work. If you just use the highest, the best metric that just gives you the best score, it doesn't work. Um, and also maybe just another alternative is you could be storing a history. Uh, and basically you could just dump all your assignments to an LLM and you can expect that LLM to figure it out itself. This is also impractical and it doesn't work because LLMs are not smart enough to find that relationship. There are more details here, but maybe if just there is more time, if there is more interest, maybe we can get back to this, but I'm gonna skip this part. So I want
Yasin
to,
Hocam.
yes,
Yasin Hocam, merhaba, Şener, from the Institute. Can I ask a question here?
yes, yes, I am.
So I'm wondering if this Bayesian search is done on which space? I mean, so we have the prompt or text in general, but what is the features of this Bayesian space? Like, is it going to be the embedding vectors for the prompt, or is it something else? Like, in which space are we doing the smart search rather than the random search?
The search is actually happening with the metric pairs, hocam. So
Hmm.
we do have. So the assumption is that we can evaluate how well they perform, how they perform on a given set of pairs and instructions, and then based on that metric,
Hmm.
we do
Hmm.
the search.
Okay, got it. I see. Is there anything like, instead of using those metrics or instructions as a space, is there anything like that in the research literature that we actually do search on embedding space, but not the embeddings of the words or the tokens, but embeddings of the, let's say, the prompts themselves?
Hmm. I haven't seen it, hocam. So
Mhm.
this happens on the prompt space, but I see your
Right.
point. And so what's going to happen with this? So what happens with this approach is you need to also sort out the credit assignment problem because
Hmm.
unlike the embedding approach, you're gonna have some bunch of prompts, and these
Hmm.
bunch of prompts they are gonna have some different scores, and you need
Hmm.
to understand what part of the prompt contributed the most to the optimal for the optimal ultimate prompt. So this
Hmm.
makes
Hmm.
it this leaves another challenge here, but this is kind of solved to like basically you just show a history of you keep a trajectory of what went well and what didn't went well so far, and then that trajectory helps you solve that matching problem. With the
Hmm.
embedding model, I guess you wouldn't uh maybe you wouldn't need to deal with that credit assignment problem. Maybe you could directly get signal what part of the prompt contributed the most to the metric, to
Hmm.
the score,
Hmm.
and then you can maybe build a kind of a Frankenstein prompt at the end, which is a
Hmm.
combination of those embeddings, and those different embedding parts, maybe they just contribute the most to the score. I'm not sure, but this would be my guess in terms of how it would look like. But I haven't seen
Hmm.
this search in the embedding space.
Hmm. Thanks, Hocam.
Welcome. So I want to a bit talk also about the practical aspect of this, how it looks like, so that or how it's evaluated, what's the performance, and does it indeed help? So the first thing is the authors in there's a couple of papers that are highly correlated to each other. So I'm just basically, but if you need a single paper, you can refer back to the one that I mentioned in the very beginning. So the benchmark they created is LangProp. There are a couple of data sets that they put into this, but I'm gonna simply summarize what they are. A multi-hop data set is it measure the LLM needs to find a few things to find an answer. So the LLM cannot jump into a conclusion straight away. It just needs to find a couple of like first a couple of steps, then it can answer the question. That's kind of the first thing that you see in this benchmark. I'm not going to just iterate them one by one. So this is like overall what they contain. The hover data set is it's a different one. In this case, LLM needs to verify the claims that require a few wiki documents. Still, again, similar to multi-hop, but it needs to first verify a couple of claims. And to verify those claims, it just needs to use some tool calls, etc. Iris dataset is the Iris dataset that we all know of. It's a standard ML dataset. It's nothing fancy, nothing different. They just want to understand, and this is going to have also some important findings there. Easy to interpret. So there is a surprising finding here for myself, which was even without examples, the grounded instructions, they often beat human engineered few shot prompts. The reason is the optimizer identifies the edge case instructions that humans usually overlook. Even if you can't just provide these, so which is the highlighted red box here that you can see with this zero shot, like basically it doesn't see any examples, but it can still come up with an optimized prompt that the human engineered prompts better than human engineered prompts. The other one is, so this result that just caught my attention. There are, by the way, some more results, but these are the ones that I wanted to highlight from the papers. This is a result on exploration versus exploitation result. Bayesian research here works because it can successfully sample the space of demonstrations rather than just picking the most similar ones. Like, why this is important? Because if you use a simple RAG system, you would just retrieve your the most similar one, and then you're gonna be okay. However, it doesn't work this way. So this is why this kind of tree search method works in this prompt space. So that's the just basic takeaway from that chart. And this one is about so there is a cherry picking problem. So maybe before I talk about this, the blue dots here that you see is they are validation scores of running with that specific few shot setting. So that's what you see with those blue points. What is important here is the performance can vary by 15 to 20%, just based on simply based on the choice of few shot examples. This is like that this is what I refer by that cherry picking problem. Even by the way, even if you use the instructions the same, no change in the instructions are just the same, exactly the same. However, you just change your few shot examples, and then you see like a lot of variations. Why this is important is because so this chart shows us we need an automated selection. So if you try to just come up with a cherry picking idea, it's not going to work. You're going to have a huge variation. So what MIPRO does in this case is that it identifies, just to remind you, like it identifies some subsets of the demonstrations, and these demonstrations minimize reasoning noise and maximize robustness. So that's the idea with that to solve that cherry picking problem. Um, so another important thing is the best uh, the best solution is the joint optimization. So that is the kind. I think one of the most important results of these works. So we can think of the instructions as the policies and demonstration as some evidences. Op and why I'm just giving you this kind of example is because optimizing them together uh, ensures the model can understand both the rule and the distribution of the data. So that is why it just leads to the better optimization if you just use better results if you just use these joint optimization uh, because this way uh, without let's say demonstrations the model wouldn't understand the distribution of data. This is another way of looking at it. Or uh, without the instructions, the model wouldn't understand the rule. So if you just try, for example, when I just first working on this stuff, I was expecting why not just simply use a simple one set of kind of hybrid method that just combines the instructions and the demonstrations. But no, it doesn't work pretty well. So, I mean, individually they work well, but when you combine them, you get the best result. So that's the output. One thing that is important here to understand is the inductive bias. That's why I mentioned that iris data is going to be important to understand some of the stuff. We know iris data is pretty much like you can come up with some rules, and then those rules can explain a lot of the story for you. So this is also what we see here. And iris data is simple so that we can understand this is indeed happening there. Um, like the iris data set, some of the tasks, not just in iris, but also the others, some tasks are rule heavy. So you need to, if you can come up with simple rules, you can sort out a lot of the problems. If, for example, if a task requires some strictly, you need to strictly adhere to the logic, like the hotpot QA, because as I mentioned, it requires a couple of steps before you find the answer. The model in these cases, the model needs the instructions to act as a constraint. Uh, on the other hand, for the pattern heavy tasks, this is what they call them, like rule heavy and pattern heavy tasks. Uh, in the pattern heavy tasks, examples do the heavy lifting. So examples play the most significant part for those problems, whereas the instructions play the most part for the rule heavy part. I mean, this is also like quite pretty intuitive. Like this, basically, this result was the aha moment for me. Um, because think of the iris data set. Uh, it doesn't matter much, right? Like if you just show a ton of those examples to LLM. Well, yeah, I mean that there are different roles in that data set, but still it doesn't make much sense. But if you can tell the model the rules that define the performance, if you have some like simple rules, it's gonna kind of intuitive that like it's gonna it would that's what that was my expectation. Like, it would improve the performance. And this also tells you why instructions matter in this optimization. On the other hand, for pattern heavy tasks, for example, you cannot come up with a simple rule, but basically the model needs to find the the model needs to find the patterns among the data. But in this case, it doesn't help much if you just try to provide the rules to the model. In that case, examples do help, which also makes sense. So, like the final finding of this framework is, in general, the data sets or the benchmarks that you have, they are a mix of combination of these different patterns. It could be rule heavy or pattern heavy, so we don't know them. But using these instructions and examples in the optimization pipeline, you can get a good optimization. So that's all the paper I think talked about. Let me see. Yes. So if you are interested in the framework, you can go to that link and you can see a bit more details in terms of how it works. Maybe a couple of just 2 minutes, maybe like I can tell you like how this helped me specifically. And then maybe we can talk a bit more if you have any thoughts. Uh, One of the weird thing, the findings is that when it goes into an optimization, similar to what Şener Hocam suggested, like in that discussion that we had with Şener Hocam, was the embedding space that I mentioned, a Frankenstein prompt. Maybe like, it can come up with something like that. But in this optimization, it can also do something similar. Sometimes one of the problems that I have observed that wasn't measured so well in the paper was the overfitting. Overfitting happens a lot if you, um, especially if you don't have a good representative instruction set or instructions question answer sets, or like simply your data set. If it's not good, like nice representative of what you're doing. If it's not complex enough, then it easily overfits your data. And how it looks like is, you see in the prompt that it tries to define each whatever happens, each like failure case one by one. It tries to enumerate them all, which is with what we don't really, what we don't want to see. uh so sometimes the prompt is not even well readable by the humans, because it is so complex. It just refers to some part of the point, like some part of the data set, some part of the failures or success cases. And in the other prompt, it just mentions, talks about the other like failure success cases and so on. So this brings you to some interpretability versus performance bottleneck. So this is what I ended up with. As it At the end, overall, this is pretty much useful. Like, I've seen results that I could never see with manual prompting or any kind of prompt engineering. So it indeed helps a lot, especially with the agentic AI components, because, for example, even defining a function signature itself is a mess itself, and let alone LLM figuring out which tool to call and like optimizing that kind of instructions for the LLM. Even a tiny little change in that prompt, in that prompt, it can break your whole system. It's so fragile. So eventually, overall, it helps a lot, definitely. But this trade-off is important. Like, I ended up with with this trade-off, performance versus the interpretability, and then I chose a point that I thought was the sweet spot for the model. So it's basic chart, but these kind of evaluations were missing in the papers. However, overall, I think this is a practical one, and also like it also like offers a simple. I think it's not, there is no extremely fancy idea here. However, it's nice, it works, and I think it's also explained. Okay, so that's it. That's all I wanted to explain or talk about this.